All right, this is example 366 on the Module 2 handout, and it's a chandelier being hung by 3 wires. If each wire can sustain a maximum tension of 120 pounds before it fails, determine the greatest weight of the chandelier the wires will support in the position shown. Okay, now before I even want to begin, I just want to sort of do a quick little free body diagram here. I'll draw it on it as well. The weight of the chandelier, I'm just going to call W. We don't know what that is yet, but that's what we're going to try and determine. Now, there's 3 other forces here, and those are the tensions in the wire. I am going to call this FAB. This would be FAC and FAD. Now, one important thing to note while we're looking at this, it says if each wire can sustain a maximum tension of 120 pounds. So some people make the mistake of setting each wire at 120 pounds to solve this problem. Do not do that. These wires are not necessarily symmetrical with each other. If they were spaced equal angles apart, that might be the case. But here you can notice that C and D are actually closer together than they are with B. That means there is a possibility here that one of the wires takes more of the loading, and as a result, it would hit the 120-pound maximum first. So we need to be really careful with this, and we'll do it in symbols first. So the first thing I need to do then is I need to figure out all my force vectors in IJK. We'll try and figure out what FAC is first. RAC is all in the XZ plane. So this is just going to be 1 foot in the x-axis, nothing in the y, and plus 2.4 feet in the k. Now, that is going to give you an overall magnitude, 2.6 feet. Now we can determine the actual force vector in symbols by using this position vector. So FAC is going to equal the unknown magnitude of FAC, which is just FAC. I'll use it in symbols because we don't know it. The I component will be 1 over 2.6. The Y component will be 0, and the Z component will be 2.4 over 2.6. So I'm just going to circle it so that we can use it for a bit later. Now for FAD, you can see here, I've shaded it in yellow, that it's basically in the YZ plane, more specifically the negative YZ plane. So the position vector from A to D is going to be 0 I hat plus 2.4 k hat feet. And this is going to have an overall magnitude, again, of 2.6 feet. And so I can now write FAD just as like I did with FAC, with the unknown magnitude and the unit vector we found from position vectors. Now, FAB is a little more complicated. I'm going to highlight it with the purple triangle here because it drops down. So we're going to have to figure out that FAB prime that's in the XY plane in order to go about figuring out our magnitudes. In order to do that, we need to know that little angle there. But luckily, we can look at it from above because that whole angle from C to B is 135 degrees. But C going around to the y-axis would be 90 degrees. That leaves just 45 degrees over the axis. So if I draw it as if I'm looking down on it, there's my x and y axes, and I put in the FAB prime, then I would put an angle there of 45 degrees. Now notice the radius too is just 1 foot, so that provides me the hypotenuse that I can now use to find the x and y equations. So taking a look at this is actually easier than it looks. RAB is going to have a magnitude of minus 1 foot sine 45 degrees for I hat, cosine 45 degrees for j hat, and we don't even have to do anything else fancy because we already know it's 2.4 feet up in the positive z hat. So I can just write it as plus 2.4 k hat feet. By the way, this gives an overall magnitude of RAB is 2.6 feet. So now I can write the force vector again with my unknown force magnitude times the unit vector. So I'm just going to quickly write that down here. Now did make a little mistake when I was writing this down here, because sine 45 and cosine 45 are root 2 over 2, but for a second when writing this down, I forgot about the 2.6 feet magnitude. So you'll see as I'm writing this down, I'll quickly correct and add the 2.6 onto the numerator, or sorry, onto the denominator right below. There we go. And then 2.4 over 2.6 for k hat. So I've now determined equations for all my forces acting on the chandelier. Okay, so now I've just written them out again here, a little nicer. Now notice the only thing I really did was for the first one, FAB, I made all the things over 5.2. That's because you had 2 times 2.6 on the bottom, so I just wanted to get basically equivalent fractions in there. And that's what I'm saying, sort of demonstrating right here, is then that 2.4 over 2.6 is equivalent to 4.8 over 5.2. Now I'm also going to put in the weight of the chandelier too, because that is another force acting on it. But of course that weight is only acting in the negative z direction. So I can write it as 0I plus 0j minus wk. So we now have these 4 unknowns, but we only are going to have 3 equations. So let's set up those equations, because when we know those forces add together, they have to add up to 0 for static equilibrium. So you're going to have to make sure all the i's add up to 0, all the j's add up to 0, all the k's add up to 0. And this is going to give us 3 equations. And I guess I better add the units in there for pounds on each of those. So I'm going to add all the x components together here. So making sure all the sum of fx equals 0. That's just going to be, I'm going to highlight the ones in yellow here. I'm going to add together and set it equal to 0. So here's my x equation with all the terms added and set equal to 0. Now I'm going to do the same thing, but I'm going to do it for all the y components. Now I'm going to highlight the ones I'm going to do here in purple, and then I'm going to add all of those up, set them equal to 0, and I'll get the following equation. Now, just to keep things consistent, I want to have the same denominator for all my terms there. So I'm just going to convert 1 over 2.6 into 2 over 5.2. This gives me the same denominator for each of the terms in those first 2 problems, and so I'm just replacing those right there. And now what I'd like to do is just simplify these 2 equations first, because you can see with the same denominator I can cancel them out, and I can get a relationship for FAC and FAD as related to FAB. Now I'm just going to repeat the process, but with all the k hat components, the z components, and set them equal to 0. When I do that, I get this. Now notice I just made everything with the same common denominator, and that's why when I subtract w there, it's 5.2 over 5.2 for that. I just wanted everything on the same common denominator, which notice I can then cancel out, leaving just the numerators there. And thus I can write FAB plus FAC plus FAD is equal to 5.2 over 4.8 W. The problem here is I have 4 unknowns, but only 3 equations. But I can also remember that the problem told me that the maximum strength any of the wires can have is 120 pounds. After that, they fail. And so let's take a look at equations 1 and 2 for a second, just to see if we can figure out a relationship between them. So because I'm not sure that all the wires will have the same tension, I can use these symbols to determine a couple of things. First off, if you're looking at equations 1 and 2, notice that FAC and FAD both equal root 2 FAB. That tells me that FAC and FAD are equal. They'll have the same tensions, and those tensions will equal root 2 over 2 times FAB. So what does that tell us? That tells us that if you're looking at it, that FAC and FAD are going to be less than FAB. Why? because root 2 over 2 is 0.7071 FAB, which means if you had FAB as a number, FAC and FAD, you'd have to multiply zero point 0.7 times that, and so you'd end up with a smaller number. So no matter what, the equations 1 and 2 tell us that FAB is always going to be a greater tension value than C or D. And that means that FAB is going to be our limiting factor here, that it's going to hit 120 pounds first, and after that, it's going to fail. So FAB is going to be the largest of the three tensions in the ropes. What that will mean is we would like to set that to its 120-pound strength. That means that we can now determine FAC and FAD, and they're about 84.85 pounds. Though I probably should write it as 60 times root 2 pounds just before, because we're not going to round off yet. Okay, so we're going to take this information and then we're going to put it into equation 3. And that way, when we put that into equation 3, we'll be able to solve for the weight. So what I would like to do here is go through the algebra, do it. It'll happen really quickly on the screen, but we'll end up getting a value for W. And for W, we will get that it is 267.42 pounds. Now, of course, we're going to round that off to 3 significant figures, which is going to give us an answer of 267 pounds. And so that's the maximum weight that the chandelier can be without causing any of the ropes to break. All right, that's question 366. If you have any problems, please come and talk to me. Other than that, have a great day, and thanks for watching.